Right, I think that's the start. So, slightly weird, slightly unusual makeup of levels in the audience, I guess. So, it's been a little bit of a challenge for me to think of how to begin, because I want to present something to you which is useful for everybody, but I think if you haven't studied quantum mechanics at some level before, well, let's say your mileage may vary, okay? So we'll go through it and we'll see what it's like. You might need to do some reading on your own. So I prepared some notes on this class, which you might want to take a look at. I'm not going to send them to you at the beginning because I want to know, firstly, how much we get through in the first session, and I'll edit these notes to kind of reflect what we talked about. Okay. Also, you know, if you're interested in reading them, you can ask me and I can send you the PDF. Right, but I'll put the notes aside for a moment and we'll just go to a presentation. Let's try this. Full screen. Okay, so I'll remember this for tomorrow, that it's actually the other aspect ratio. Right. So like I said, today, the first thing we're going to do is we're just going to refresh our memories on quantum mechanics, or potentially learn some quantum mechanics. Okay, what is quantum mechanics? Quantum mechanics is a theory which describes everything that's very small. Okay, so we're talking about interatomic interactions, subatomic particle physics, and really, quantum mechanics is a very successful theory. It describes the world very accurately and also fundamentally. So what's the difference between classical mechanics or classical physics and quantum mechanics? Well, there's two big differences, at least on the surface level. The first is that classical mechanics is deterministic. So when you think of predicting what's going to happen when I drop this cup, okay, you know exactly what's going to happen. It's deterministic. What happens happens because of it follows the laws of physics. In quantum mechanics, it's a deterministic, it's a probabilistic theory. So effectively, everything is statistical. Okay, so if something happens, it's not guaranteed to happen. It's more likely. It's more that thing is going to have a probability of happening. The next thing is in the name, quantization. Quantum mechanics reflects a picture of nature where everything is divided into discrete pieces, discrete chunks. Okay, unlike classical continuous physics, where you can divide something forever into smaller and smaller pieces. So what are the postulates of quantum mechanics? Firstly, we've got this. So what are postulates? I guess postulates are statements that we hold to be true. So the state postulate states that everything we can know about a quantum system, so an ensemble of quantum particles, is held within the state vector. So the state vector, I'm going to start writing and drawing stuff, I think. The state vector is just a vector where we have some numbers. Let's say that this is our state vector. It's a vector, and it's got it's a set of numbers which describe everything there is to know about the state of the system that we're in. Okay. The observable postulate. Every observable corresponds to a Hermitian operator. Okay, what is a Hermitian operator? A Hermitian operator is if we have a matrix, so we have a matrix, so we've got some, let's ignore that these are the same letters. We've got some letters. If we diagonalize this matrix to get the eigenvalues of the matrix, what we'll find is that those eigenvalues are real. Okay, even if these numbers, if this matrix is complex, the eigenvalues will be real, and also the eigenvectors of the matrix will be orthogonal, and also we can say that this matrix is adjoint. So if this is the matrix, we can say well, you know what adjoint means. We need to go a bit faster. Okay, measurement postulate. So this basically means that if we have an operator, if we want to extract some information from the system, if we effectively want to take our system and measure something, we apply an operator, for example, A. That means that our system is going to collapse into an eigenstate of that operator. Okay, so this is all just linear algebra. Quantum mechanics is just linear algebra. Finally, the evolution postulate states that the system, the time evolution of the system is governed by the Schrödinger equation. Okay, we'll talk about the Schrödinger equation in just a moment. But firstly, we're just going to speak about something a little bit more abstract and mathematical, which is Hilbert spaces. And this is a tool that we need to understand in depth to apply further methods in quantum mechanics. So basically, a Hilbert space is a vector space. So it's a space where you can have a vector of n dimensions, where the length and angle between those vectors can be measured. Okay, so in real space, I don't know why. In our three-dimensioned world, we can have a couple of vectors, okay, and I can say that vector has a length, and I can say that it has a direction, which I can measure, and I know which way they're going to go. A Hilbert space has n dimensions, okay, and it has a dimension for every degree of freedom of the system. So if we have one particle, that particle has three degrees of freedom, and so our Hilbert space has 3 dimensions. If we have 2 particles, it has 6 dimensions, etc. Okay. So what are the properties of Hilbert spaces? So it's got an inner product, so effectively a dot product. So if this is a vector and we've got another vector, if we want to take the dot product of those 2 vectors, we're going to call this one A, I'm going to call this one B. Sorry, I don't have very many letters today, I'm just doing A and B. Okay, this is the dot product, it's the inner product of these 2 vectors. I guess you know what that means, everybody knows what that means, right? Okay. Completeness. If we have a vector and we line it up with another vector, and then we put a third vector and we put several vectors in a line, completeness in this space means we can draw a line from the beginning to the end, and that will tell us the overall direction, magnitude and direction that we've gone in our vector space. Okay, completeness. Separability just means if I have a vector and I want to approximate that vector, I can take a whole load of other, I don't know, whole load of other, basically a basis of vectors, and I can approximate that vector as a sum of all of these countable vectors. So I can number them, okay, and I can add them together in some quantity, and I can get the vector I'm trying to approximate. I can use a basis to approximate a vector. Orthogonality and orthonormal, I think we know what that means, okay? If you don't, I don't know. All right, orthogonal, okay, there is no component of this vector represented in this vector, they're orthogonal, okay? Orthonormal just means that the lengths are 1. Right, examples of Hilbert space. Okay, so Hilbert spaces can be real or complex. In general, in quantum mechanics, we're going to be looking at complex Hilbert spaces. So we need certain things to be able to represent quantum mechanics. We've already talked about some of them. one of them that we haven't talked about is superposition. So superposition is an important concept in quantum mechanics, and this can be represented in terms of vectors within the Hilbert space. So effectively, we can take a vector as the sum of a linear combination of two other vectors, and this is a superposition of those vectors. Okay. Okay, this is important. Operators as linear transformations. So I'm going to run out of space here. There's not a lot of space. So linear transformations. What we effectively can do, I'm jumping ahead here. Okay, that's an inner product, so it's a dot product. We can apply an operator in the middle. Okay, we'll talk about this later. It's called Dirac notation. Right, so we're applying this operator. What this gives us is a matrix which represents this operator. Okay, so this is going to be a matrix like this, and so we'll say this is that matrix. So we've got a matrix. We can take this matrix and we can write this matrix as a vector. So we'll call that V multiplied by some eigenvalues. We'll call that lambda multiplied by V transpose or V conjugate transpose. Okay. So this is a whole load of basis vectors multiplied by some eigenvectors multiplied by some basis vectors. We've eigendecomposed that matrix. Okay. By writing it like that, we've assumed certain properties of that matrix, but we can write it as an eigendecomposition. And what we're effectively saying by operators as linear transformations is that we can stick that inside of here. We can say we've got some eigenvalues of that matrix, and we can take an outer product. We can take an outer product V, something like that, and we can write the whole matrix in terms of the eigenvalues. Okay. Yeah, spectral theorem. Yeah, all right. Maybe I was talking about spectral theorem, but whatever. Okay, I think we need to move on a little bit. Right. Another thing that's important in quantum mechanics, if you've never heard of this before, then we're going to struggle. But the Heisenberg uncertainty principle basically means that you can only measure to a certain precision in the real world with respect to another observable. So if we have a thing that we want to measure the position very accurately of, then if we measure that position as accurately as we possibly can, then we cannot measure the momentum very accurately at all. Okay? If we want to measure the momentum of the object, we can't measure the position. And we've got the same kind of deal with the energy and the time. So this is just a fact of the quantum world. Measurement, trying to measure something accurately means that you can't measure other properties accurately. So you might ask, why is the Planck length involved? Why is the Planck length involved? Well, you notice it's over 2. Okay, so the fact is, if we're thinking about waves, then if you have does everybody know the Nyquist theorem, the Nyquist spectral theorem? Okay, maybe we'll move on. Okay, but effectively, just if you don't know this, the fact is that if you want to measure the energy very accurately, you can't measure the time very accurately. If you want to measure the position very accurately, you can't measure the momentum very accurately. Right, that's out of the way. We're gonna talk about the Schrödinger equation. Going to go through a couple of examples quickly, and then we're going to sort of go on to what this course is supposed to be about. So, the Schrödinger equation is the equation of motion of quantum systems. In its most general form, in its full form, it's time dependent. but for most of what we want to consider, we don't want to consider time. Okay, we want to ignore time, and we want to assume that time is static, and we're just dealing with the time-independent Schrodinger equation. So if we're looking at the time-independent Schrodinger equation, what we have here is a differential equation, but written as an eigenvalue equation. So we've got an operator operating on a state vector, which is our wave function. And when that operator is applied to the state vector, what we get is an eigenvalue of the energy, okay, multiplied by the state vector. Okay, so if we want to apply the time-independent Schrodinger equation to some basic systems, we can start with I keep losing things here. There it is. Right. Right. So effectively, what we're doing here, I'm going to write. Can you read that? Well, it doesn't matter, does it? So, in one dimension, we've got a differential operator, and we're assuming that we're only dealing with one dimension, so we're going to write it not as a partial differential. Okay, and we've got a state vector, a wave function in one dimension, and we've got some potential equals. Okay, so effectively, we've got to write our potential, and that determines what system we're trying to calculate. So in this case, if we look at the particle in a one-dimensional box, our potential just looks like this is infinity, this is 0. So effectively, we have a box with infinitely high sides on both sides. And what we're doing is we're putting a particle into that box, allowing it to resonate, allowing it to exist as a standing wave within this box. And we look at what energy levels we get in this box. And what we find is we get, that's very poorly drawn, whatever. We get a bunch of sine waves as standing waves in that box. Okay, and those sine waves have energy levels associated with them, which are associated with effectively the harmonics of that sine wave. Okay, so I don't know. Maybe we should briefly. Okay, I think briefly we'll just look at how we get. Briefly, we'll just look at how we get from the equation to some energy levels. And I think what we'll do is we'll simplify one more, and we'll say that our potential is 0. Okay? We'll say that our potential is 0. And so effectively now what we've got is a wave equation. Okay? So our wave equation is just that. And so what we've got, excuse me, what we've got is effectively a second differential equals some energy level, some eigenvalue multiplied by our wave. Okay, so if we've got no potential, what does that mean? It means that we've got a free particle. So if we allow the particle to move in space anywhere in the world, anywhere in our 1D world, no potential, we've got a free particle, this is that situation. Okay, so if we want to solve this differential equation, well, we know that this wave equation has a trivial solution, and we can just write it down. Right? We know that our wave equation is solved by a sine wave. Okay, it's solved by a wave. So if you put in a potential, what you find is that you just get a slightly modified second order ordinary differential equation, and you have to solve for the wave function, which is our eigenvectors, and the energy levels, which are our eigenvalues. Okay? I don't want to dwell on this. I don't think we've got enough time to really dwell on it too much. But this is what happens in quantum mechanics, right? We have a wave equation called the Schrodinger equation. We have a potential, and the potential determines our system. We put the potential into the system, and then when we solve for the eigenvectors and the eigenvalues for that potential, we get our results. Okay? And there's many, many, many of these systems. The infinite potential, the finite potential. So in the finite potential, this is demonstrative of another property of quantum mechanics. If instead of having infinite barriers, we only have finite barriers, so our barriers only go up to potential V0, and this is still at 0. What happens is we still get our trigonometric solution in the middle. We still get our standing wave in the well. Okay, but badly drawn again. Maybe no, never mind. But what we get is some amount of tunneling into the barrier, which is represented by this exponential decay. Okay, and so this is the first property which is obviously and demonstrably and visibly different from classical mechanics. Okay, so the fact that some of our particle, we've only got one particle here, it's a standing wave, but some of it, probabilistically, it has some probability of existing within the barrier. Okay, which is kind of weird. Right? Right. So that's one thing that exists. Another thing that we can think about is if we have a potential which looks like this, again V0, but this time the potential's in the middle and we have zero potential on either side. If we just look at this part, we can say, right, we've got a free particle in space, and now what we get in this barrier region is some sort of decay. And on the other side, we've got a mirrored image, and we get some kind of decay. So what this means is we've got a non-zero probability of being anywhere in the middle of the barrier. It still decays exponentially into the barrier. But effectively what this means is if a particle was on this side of the barrier, there is a non-zero probability of it tunneling right through the barrier and going to the other side. Okay? And so when you hear about tunneling in quantum mechanics, what that really means is a mathematical concept of the probability of a particle going either into a physical object or going through a physical object, which is higher than the amount of energy the particle has. Okay, so what we have to say is that this particle does not have enough energy to classically go over the barrier. Okay, it doesn't have enough energy to go over the barrier. It's got less than V0 kinetic energy. It's just that quantum mechanically there is some probability that it will go through the barrier. Okay, and so this comes straight out of solving the Schrodinger equation for the step potential. All right. So we don't have enough time to actually do it because we've got other things to do, but we can talk about some of the examples, and if you want, if anybody actually wants to know how this is done, you can sort of come to me and we can just solve it on paper. It's pretty easy. Okay. Right, so that's what we just said. I don't think we need to go into more detail. So what we're interested in solving is potentials which exist in the real world in material systems. What are material systems? Material systems are macroscopic pieces of stuff, okay, macroscopic, something big enough that you can interact with in a classical sense, made up of atoms and, of course, electrons. And those electrons form potentials, okay? They form potentials. So what we want to be able to do is to simulate those atoms on a computer and to predict the properties of those materials, those macroscopic materials in the real world. And in order to do that, what we need to do is to simulate the potentials and solve the Schrödinger equations with those realistic potentials. One way we can do that is by gradually stepping up the accuracy. So we can go from having a finite potential well, right, which, traps our particle, to something which is more looks more realistically like an atom, like an atomic well. Okay, so we can go to a harmonic oscillator. Okay, so what we know is that if your particle is sort of if your particle is in a nuclear potential, we've got a 1 over r potential. Okay, so our potential looks like, right? So that looks a bit more like that than the square box. Okay, so we can step up towards realism, solving systems slightly more complicated each time until we get something which resembles reality in some sense. So the harmonic oscillator is just x squared, okay, and we can solve analytically the harmonic oscillator, and what we get are, again, eigenvalues and states, okay, eigenvectors, wave functions, which look like this. Okay, similar situation, very similar situation. Right. So when we solve the Schrödinger equation, what we get are a bunch of quantum numbers. Okay, quantum mechanics is quantized. There's a bunch of integer variables that exist, and they define the system. Okay, we have the principal quantum number, which defines the energy level of the particle or the electron. Okay, we have the orbital angular momentum quantum number, which is L. Okay, magnetic quantum number, and a spin quantum number. Okay, these come out of solving the Schrödinger equation for a hydrogen atom. Okay, so what I want to say, if you've never studied quantum mechanics before, is that once you've solved the Schrödinger equation, once you've got the eigenvalues and eigenvectors, effectively what you're given, what you've found is a solution for any state. Okay, so if I have, for instance, some potential, and I've got some sort of ground state energy, and then I've got a maybe I should have a higher frequency, whatever. So we've got two states. One of them is the ground state, and one is the excited state. Okay, these have numbers associated with them. Okay, so we can say that this is n equals 0. This is n equals 1. Or n equals. I need to drink my coffee. So what we can say is you can't have intermediate states. It's the same as a classical system where you have a standing wave. If I take a piece of string and I fix the piece of string at both ends on my hands, and I say this piece of string has these two nodes which are not going to move, but I'm going to excite this string in a way that it's going to form a standing wave. So we're going to have a standing wave. There is only a certain number of standing waves which can exist on this string, right? It can only oscillate in particular ways, and that's because we need solutions which have nodes where the string is fixed. Okay, and it's the same in quantum mechanics. The solutions to our equation of the electronic density are standing state solutions to the equation of motion of the electron density, and they have particular solutions associated with standing states. Okay, so this is what these quantum numbers are. They just determine the numeric index, effectively, of a standing state solution. Right. Good quantum numbers. So, if we label these standing state solutions of our system, then we want what we get is a solution to the Schrodinger equation. Okay, so if we also take our solution, which is our eigenvector, and we apply an operator to that eigenvector, what we're effectively doing is we're asking to predict an observable. Okay, so in this case we've got a Hamiltonian, but we could have another operator here, and do they commute? What is going on? So I think we just have to accept that some of these things we're not going to learn today, right? If you know it, you know it. If you don't, then you can read about it. Okay. All right. So the problem that we have in quantum mechanics is that there's a limit to what we can actually solve. Okay, there's a limit to what we can actually solve, and the reason is because if I have a differential equation, in some number of dimensions, it becomes the solution becomes unknown, the general form solution. If we're dealing with 1D differential equations, we can just say, well, this looks like a wave equation, or this looks like some other differential equation. I'm just going to throw a general solution at it, try some solutions, modify them a little bit, get my result. Problem is, as you start adding more dimensions, as you start adding more complexity to the system, it becomes either impossible to solve, or the solution is unknown, or you have too many degrees of freedom to deal with. Okay. The limit of what we can actually solve is the three-dimensioned Schrodinger equation. Okay. So what we can actually solve is the hydrogenic atom. Okay. So if we have a 1/r potential, we can throw this 1/r potential into the Schrodinger equation, and we can solve the Schrodinger equation for the hydrogenic atom, the 1/r. And so what this is a three-dimensioned problem. So effectively, we've got an origin. We draw some axes, and we say that as we go towards the origin, 1/r is the potential we experience in the radial direction towards the origin. Okay. What is the potential in the angular directions? It's isotropic. Okay, it's 1/r everywhere. Okay, so it doesn't matter which angle we go in; it's always 1/r towards the center. And as we add more dimensions, what we find is that we need to be careful about the coordinate system that we're dealing with. Okay, so we could just say that our differential operator is the Cartesian equivalent of the 1 over x one-dimensioned system that we were looking at earlier, and just extend to the 3D Cartesian coordinate system. Okay, the problem with that is it makes it very, very difficult to solve in practice. Okay, what we actually do is we take a spherical coordinate system. So instead of saying x, y, z, z, whatever, instead of this kind of coordinate system, what we do is we say we've got a point, and we have a distance r associated with it. We've got an angle, which, if we imagine this is a plane, imagine we have a plane with an axis sticking out of it. The angle going around the plane is that angle, okay? And then we say we've also got an angle like that, okay? So effectively we've got the angle which goes around the world, and we've got the angle which goes north and south, okay? So theta and phi. And so we can write our Laplacian, our second differential operator, in such a way so that we have so that we write it in spherical polar coordinates. We've got an r direction, a theta, and a phi direction. Then we can separate this Schrödinger equation. We stick the Laplacian in spherical coordinates into our Schrödinger equation. Just replace the Laplacian with the spherical version. And what we can do is we can separate into the 3 coordinates. So we can have a separate problem in radial dimensions and a problem in the angular directions. Okay, so if we look at the radial Schrödinger equation, what we end up with after the process of separating out the variables is something like this. Okay, so what we've got is another 1D Schrödinger equation to solve because our coordinate system allowed it to be separable. Okay, so effectively all we've got here is the wave function, the radial wave function, go away, a potential which is not there. We've got a potential which is here, and we've got our a second differential operator. Okay, so that's what we do in the Schrödinger equation. Okay, all we've got to do is make sure that our potential is the Coulombic potential. Stick it into the Schrödinger equation. We'll get a radial Schrödinger equation to solve, and we'll get an angular component as well. Right. So here's the whole thing. We've got, you can see the radial part of the Laplacian. This is just the angular part of the Laplacian. We separate everything into radial components and angular components, and all that means is that we can write our wave function as a product of the dimensions, two functions of the dimensions. Right, and what we get once we solve for the radial component, we get the radial component, and once we solve for the angular component, we get the spherical harmonic. Okay, so what are the spherical harmonics? If you haven't heard of the spherical harmonics before, effectively, if we have a point a particle, and we say that this particle exists in our radial coordinate system, right? We've got a radial direction and an angular component. We take the angular component away. Okay, we ask, on this sphere, we effectively have the component of the electron density, which is projected onto the sphere. What standing wave solutions do we have in those two dimensions. Okay, so the same way you can have an oscillating string and a standing wave. You can take some electron density and you can say in 2 dimensions, in 2 angular components, what are the two what are the standing state solutions of our system? Okay, and these are the spherical harmonics. Okay, so what I've done is I put some notes together, and I didn't really know what you would want for an introduction to quantum mechanics for the first hour. So I solved the spherical problem, and I put it in the notes. Okay, so I derived the spherical harmonics, and I derived the radial solutions to the hydrogenic atom. And so what I'm proposing to do is just to show you sort of how it works. And if you're interested and you haven't done this before, you can look at my derivation in the notes, and maybe that'll be helpful. All right. But effectively, once you derive these solutions to the hydrogenic potential, what you get is the energy levels of the hydrogen atom. Okay, and these are the same energy levels that were derived by Bohr, sort of pre-Schrodinger equation quantum mechanics. All right, so it matches what was expected for the hydrogen atom, and the total wave function is just some radial function multiplied by the spherical harmonics. Okay, and our radial function has some nodes, so I don't know. It has some nodes, okay, as we expect for the hydrogen atom. Okay, and you can get that straight out of solving the Schrodinger equation for a hydrogenic potential. Right, and this is what we actually get. So the nodes in the radial solution come from Laguerre polynomials. So I've also derived the Laguerre polynomials in the notes. So if you haven't done that before, you can have a look at that derivation, and that'll give you some sort of mathematical clue as to how we get from the Schrodinger equation to this solution. Right. But one thing to take note of is if we ignore the nodes, the nodal part of the radial solution, basically our radial part decays exponentially. So we've got basically an exponential decay coming from this term, and we've got some constant term. Right. So solutions to our Schrodinger equation for the hydrogenic atom, basically 3 components: a nodal part, an exponential decay, and a constant associated with the quantum numbers of our system and the charge on our nucleus. Spherical harmonics, the angular part, is basically just an angular momentum quantum number multiplied by what am I saying? The solution to the angular part of the Schrodinger equation is the spherical harmonics as our states, and this is the eigenvalues of our angular part. Okay. All right. So we've got a break. I'm not going to labor this too much, right? What I decided was at the last minute that we're going to have a little bit extra of this kind of background to quantum mechanics. But I think it's probably not that useful for anybody. Most people have already done it, or they are not really learning anything from this. So I don't think we're going to take this too far. We'll probably just go on to the main part of the course pretty soon in the next few minutes. But anyway, we'll have a break, and then we'll come back.